Welcome, everybody. Thank you for joining me today. My name is Ronaldo Pinto. I'm the Technical Sales Director for Applied Flow Technology. My email is ronaldopinto@aft.com, and I'll be hosting today's webinar that we have titled Evaluating Dynamic Loads and Piping System Costs by Waterhammer, Part 1. If you, during the presentation, have any questions, you can type it in the chat room of GoToMeeting. And at the end, we'll have a session of questions and answers that we'll try to answer all your questions. If we don't have time, you will receive an email with an answer to your questions. So first, let's have a brief look at the webinar agenda. We'll be talking about the Waterhammer causes, Waterhammer imbalance forces that are generated by the pressure surge, Waterhammer software like Impulse, how it's used, calculating imbalance forces, the hand calculated imbalance forces method commonly used by pipe stress engineers, AFT Impulse and how it calculates the imbalance forces. We'll be working with the model with AFT Impulse to see how we can generate these imbalance forces and export it to a pipe stress program. We'll talk a little bit about code compliance, how to use it, and generating the dynamics force data that we will then be exporting to a pipe stress program. In this case, we'll be using Caesar 2 as the pipe stress program that we'll be exporting to. And as I mentioned, we'll have a session of questions and answers that we will try to answer all your questions. So Waterhammer can be caused by many events, which we including valve closure, opening, closure and opening. But it's important to highlight that not only a full closure of the valve can generate Waterhammer, also a partial close of the valve can generate Waterhammer in the system. Also, pump speeds change. Not only the trip of the start or the startup of the pump can generate Waterhammer, also pump speeds change can generate Waterhammer in your system. Relief valve crack opening is another one, a source of possible generating Waterhammer effect. And another one that can be cause Waterhammer effect is a rapid change in tank pressurization. So Waterhammer causes transient event forces in piping systems. This is a result of a fast-moving pressure wave in pipes. When you change the flow due to a valve closure, for example, that kinetic energy becomes a high pressure at the location and starts traveling upstream where the flow was closed. Elbow pairs are especially susceptible to imbalance force due to the change of directions and the flow directions of the system. And it's important because this imbalance force can be seen by the supports that you design, and they need to be able to handle these forces. This is the main concern, one of the main concerns of the pipe stress engineer. Waterhammer software. Waterhammer is a sufficiently complicated phenomenon. It's not easy to model, especially when you have a pipe network. And in such cases, a modeling software can be very helpful, and it's usually required to accurately model the Waterhammer event. Typically, the issue of primary interest of the engineer is understanding the pressure streams, how they are generated by the pressure waves. This allows the selection of the spike strength and design for equipment protection and general safety in your system. AFT Impulse calculates a pressure flow, the transient pressures and flows, and this information is useful to predict the transient imbalance forces that we then use to calculate the stresses in your system. So how does imbalance force generated by the Waterhammer event? During steady state between elbow pairs, there's an balanced static pressure force that is exerted on each elbow along the axis of the pipe. It's imbalanced, it's not moving, which the force is equal to the pressure multiplied by the inside area of the pipe. Now, consider an event where the flow has been stopped downstream by any cause, like closing a valve or whatever, a pump trip, or this originates a pressure wave that travels opposite to the original flow direction. During a short time of duration, one elbow of the pair sees the elevator pressure while the other one does not. This results in a net differential force acting on the elbow pair that can be quite significant. Once the elevator pressure reaches the next elbow, the pressure equalizes and the differential load between the elbows disappears and it appears in the next section of the pipe. So let's see an event here that we have here. We have flow in this direction, normally in steady state condition, and we close a valve right here. So this kinetic energy by Bernoulli equation becomes a pressure, and it starts traveling up. And when it reaches this elbow, it generates a high pressure on this side. And this pair of elbows sees a low pressure on this side. So we have high pressure here, low pressure here. This generates imbalance forces that act on this pair of elbows until this pressure wave, high pressure wave, reaches the other elbow. So it's an dynamic equilibrium again. And so this section starts to see the imbalance force as the pressure wave travels upstream the pipe. There's a common equation that is very useful, especially used by pipe stress engineers to calculate the delta P generated by the pressure wave. It's called the Jacobi equation, and it's used to predict the delta P that results from the transient event that occur instantaneously. This equation is established as the delta P is equal to the fluid density times the wave speed times the change in velocity. This delta P pressure is added to the existing static pressure at that location to determine the maximum theoretical pressure in the pipe. Now, this equation is very useful, but it works best when the flow fully stops and the closure is quickly. But complexity in the real system quickly rendered this hand calculation useless. What happens if the valve is partially closed? How do pipe with inline components that generate wave reflections add or subtract to the pressure wave that is traveling? What about other forms of energy transmission like friction losses, momentum changes, area changes? AFT Impulse, as we will see, automatically accounts for all these elements in the force imbalance calculation. AFT Impulse can calculate imbalance forces in a system based on transient pressures. Calculated forces can be plotted, as we will see later on in graph results window. You can examine the forces. Calculated forces can be exported in a force time data files, which then can be imported into a pipe stress program application such as Caesar2, Roar, and Triflix. Right now, we're working with Bentley and K-Pipe to create an interface with Autopipe and K-Pipe. Hopefully, we'll be offering it soon. So we're going to be working with the Hammer model in Impulse that I called Hammer. In this event, the cooling water supply line shown above suffers a pressure surge when the turbine-driven pump trips due to a varying temperature profile. So what we have here is we have a sudden closure here. So a high pressure is generated in this area, and pressure wave starts traveling down upstream the system in this direction. It is requested to the engineer to calculate the overpressure of the pipe and verify the code compliance. The system is water, 140 degrees Fahrenheit, mass flow rate 130 pounds per second. The supply pressure is 250 psig. The design pressure is 350 psig. All the pipes are 8 inches, schedule 40, and the pump trips in 0.2 seconds from zero, that it's 100%, to zero times in seconds that it's 100%, and 0.2 seconds that it's zero. So once the overpressure is calculated, what should the designer do with this value to verify code compliance? Well, the answer to this question depends on the code you're using, of course. B31.3, SAME B31.4, pressure transportation systems for liquid hydrocarbons and other liquids, refers directly to the maximum value of the overpressure, and it establishes a limit of 10% above the design pressure. When we're talking about SAME B31.3 process piping code, B31.3 refers to the maximum stress produced by the loads created by the surge pressure, establishes that it should not exceed 1.33 SH, where SH is the allowable stress for the operating temperature. So let's imagine we're working with B31.4 and AFT Impulse. So if you're working with B31.4, you first have to calculate the allowable pressure by the code, which is 10% above the design pressure. For this example, it would be 385 psig. Once you establish that, then you set the design alerts to detect this value, making sure it's not violated during the transient event. To do this, we go to the design alert manager. We create a design alert for that we call maximum B31.4 maximum allowed pressure. We apply it to all the pipes, and the value of it would be 385 psig as we established in the presentation. So I'm going to bring AFT Impulse to show the example that we will be working with. So here we have the pump trip in this event right here, and we will see the pressure traveling in this side in this sense. As I mentioned, it's a fluid's water. So let's open the event here. So now we have the transient event in this sense right here. So the pump trips as established in the presentation, it trips in 0.2 seconds from 100% to zero. Since we're working in this case with B31.4, we go to tools. We want to start the design alert. We come to design alerts, and you can see that I have created a design alert for B31.4 maximum allowable pressure. Established as a maximum of 385 psig, and it's established for all the pipes in the system. If we open any of the pipes, let's open P5. there's a tab that you will see there, and here that it's design alert. So we are applying to, you can see that the design alert is applied for the for a pressure of 385. If it exceeds that value, we'll receive an alert from the program. Okay, so we're going to run it now. We check if everything is set. We have to establish the sectioning. We establish the sectioning here. So now it's all set. It's in green, ready to be run. We run it. It's almost done, 82%, 87%. We go to output, and here we see in the, it's a tab that design alerts, and it's telling us that in pipe 5, pipe 6, pipe 7, from pipe 5 to pipe 11, the pressure warning is exceeded, the align alert. So let's take a look at one of those pipes. So we go to graph results. We select one of the pipes that it's telling us. I'm going to select pipe 6, for example. I'm going to examine it in 1 second. This pressure static. So here, I'm going to add the design alert maximum and establish PSIG. So now we see here that the design alert is right here telling us it's 485. And we see that initially, in the initial cycle, the pressure wave is violated. So a solution needs to be found to comply with B314. So we can see that we don't, we can check if we're using code B314, you can check it whether or not you're complying with code using AFT Impulse without any other program that it's needed. Now, if you're using B313, you have to calculate the imbalance forces, and since the code does not talk about an allowable pressure, it talks about a level of stress. You have to export it to a pipe stress program in order to see if you comply or not with B313. So the first thing you have to do in Impulse to generate the forces and then export it to a pipe stress program is define the force sets. In order to process the data, the location of the forces must be calculated and defined. So here we have the example from Impulse. So before I go on, I would like to explain what we're going to do. We're going to analyze the forces in the longest pipe, because it's not that these pipes are not important, but since the pressure wave does not last long in each one of them, the imbalance force does not pass very fast, and so generally it's a major concern for the pipe stress engineers, the longest pipes. So in this case, we're going to analyze from we're going to create a force set from this part to here. That would be from node 45 to 75, which is pipe 5. It has 90 feet, and another one that we're going to analyze is from 90 this long pipe here from node 90 to 110. It's a pipe 2 that has 75 feet of length. I have added here the coordinates from Caesar because we're going to use it to export, determine this in what axis the force is applied. And another thing is, for impulse, it is positive in the sense of the flow. For in the case of Caesar, like here, this would be X. For impulse, it would be positive in this direction. For Caesar, it would be the contrary. So what's positive in the X direction for impulse, it will be negative in Caesar. So we have to multiply it by -1 to apply the forces in the correct sense. So this is what we're going to do. We're going to create a force set. The first force set that we're going to create is in this pipe, in pipe 5. We're going to call it 45 to 75 to reference to the nodes that's being applied. And as I mentioned, it's going to be applied in the minus direction because for impulse, the positive direction is in this sense, and for Caesar, it's in the opposite sense. So we multiply by -1 to properly apply the sense of the load reported by impulse. The other force set that we're going to create is from 90 to 110. We're going to call it force set 90 to 110. And the same thing, it's going to be applied in -1 direction and the -x direction because for impulse, positives have in this sense, and for Caesar, positive is in the contrary sense. Force sets and impulse are defined at the output tab in the transient control window. For each force set, the user must specify this: a start pipe and an end pipe. So here we have two force sets that we're going to create: 90, 110, 45, 75. Since it's one pipe for each one, for 90, 110, it will be pipe 2, starting at 0 and finishing, it will be pipe 2 at the end of the pipe. For force set 475, will be applied it in pipe 5, as we saw in the previous slide, from the starting point 0 of the pipe 5 and at the end of pipe 5 that has 90 feet of length. Then, and this is new in impulse, you have to define the unit vector for each force set. That way, when the pipe stress program knows what sense the flow forces are going to be applied in. So as I mentioned, the coordinates will be -1 in the X direction and 0, 0 in the Y and Z coordinates. So when we will see that Caesar will receive this and it will know, you don't have to specify what the forces, the sense of the forces are being applied because you're indicating it directly before you export them. So, and after that, you can graph your forces result before you export it to examine how the forces are being generated to see if they make sense. And then we'll see how to export it to a pipe stress program. So let's move on. I'm going to come here. I'm going to bring the other scenario. Here we have a pump trip, as I mentioned here, right here in this part here. The pump trips happen here, and the pressure wave is traveling in this direction. We're examining this force set here and this force here from 90 to 100. So to create the force set and indicating where it's being applied, we go to analysis setup. We go to force and see here that force set 4575 is applied in pipe 5 at the beginning and the end of pipe 5. Force set 9010 is applied at pipe 2 at the beginning of pipe 2 and at the end of pipe 2. And the last step that we have to indicate is the sense that the force is going to be applied. So we said it's in the minus X direction. So we indicated here 0, 0. That way Caesar will know what the sense to apply the forces when it imports it from Impulse. So we're ready here. We hit OK. We run the model. We're running it, the transient event, we're analyzing it for 10 seconds, but generally all that time, the time force set is not needed, all that data. And we see that only generating the first second will be enough. We go for output. There's a tab that is forces. It tells us that in the first force set, the maximum force applied is 3,675 pounds. And in node 100 and the second force set, 910, it's 3,442. This would be enough to design if you're going to design a restraint on your pipe system to control those forces. So this would be what you would be reporting to the civil engineer. Now we can go to the graph results. We go to forces, and here we have both force sets. We can see it here. We're going to check all times. And we can see here that the critical point is where the maximum forces occur. And it occurs here in the maximum force occur almost, let's see, at 0.1 second. So we can set the time because the interest is, so we're going to see 1 second generate. And now here we can see the force sets are maximum at, let's see, it's the 3,600 occurs in 0.1 second. And another thing that we can see is that force set 4575 is is higher at the first cycle, but then force set 110, which is the longest pipe, is the forces are higher at that point in the subsequent cycles. Okay, so now we saw the forces, force imbalance generated. We're ready to export to a pipe stress program because as we indicated, B313 talks about a level of stress, or allowable level of stress. So we want to see if we comply with code. So as I mentioned, we're going to export to Caesar. There are 3 types of dynamic analysis you can use to calculate the stresses caused by the pressure surge. Static equivalent, spectrum analysis, and time history analysis. In this webinar, we will use spectrum analysis as an example. In the part 2, we will cover the different type of analysis in detail, and we'll see the details of how to export it to Caesar. But here we'll be working with spectrum analysis. So first, in Impulse, to export the force sets, the force generated by the pressure surge, we select export Caesar2 force file from the file menu. We select the force sets that we want to export. So here we indicate the ones we want to export to. And then before we move, Caesar2 has a limitation. Since Impulse, we can calculate the force imbalance for a longer time. Caesar does not need that because, as we saw in the example, the highest forces are generated in the first timing of the event. We don't need the whole thing. So Caesar has a limitation. It can only import up to 2,500 data points. And as I said, Impulse can generate forces with much more than this because we can analyze an event for a longer time, but Caesar does not need that. When more than 2,500 points are generated, the user needs to adjust data set to be exported. Usually the transient event of interest, the stress analysts are less than a few seconds, that's what we saw in the graph. So in this case, 0.9 seconds from impulse analysis duration can often be quite easily narrowed to specify the prime of interest. So we come here, we come to File, Export Forces, we select Caesar, and we select the force set that we're going to export it. 4575, this first force set, and 9010, second force set. We want to export it both. But here, if you see here, it's bigger than 2500, the data point. It tells us in red that Caesar will not be able to receive it. So we have to limit. Let's try 1 second. The number of data points is 2,800. Caesar has a limit of 2,500. It still is too much. So let's go to 0.9. 2,500 to 22, we're very close, but still not there. Let's go to 0.85. So now it's in blue. It can be exported. Perfect. Now, the second step is selecting the type of analysis you're going to perform, whether you're going to perform spectrum analysis or time history analysis. The difference is basically because of the different way both analyses are done. So it will take different actions depending on the the analysis you're going to do. If you do a spectrum analysis, which we will be doing in this webinar, AFT Impulse will generate one FRC file with all the forces selected in one file. If you do a time history analysis, AFT Impulse will generate multiple FRC files, one for each force set selected. Let me bring Impulse. So here we select spectrum analysis. We say export. It asks us to give it a name. I already created one that it's called both, and this is the one we're going to be using for Caesar. So it's ready. It's already done. It's ready. So it's exported. We close. Now, how does Caesar receive it? To import it for Caesar, what we do is we use the utility that's created in Caesar. Caesar has an interface with AFT Impulse. This will launch a window where you can browse for the force set that you generated. Here are both force sets, nodes 45 and 75, and force set 90, 110. We tell it where what nodes we're going to apply it with to. And once you do that, each of the force files loaded in this example will be used by Caesar 2 to create a DLF curve, a dynamic load factor curve, that Caesar will use to predict how each natural frequency in the system will respond to each load. Unless you specify the unit vector for each force set, which we did previously before we exported, when Caesar finishes the selection, it will warn you that the force set time file that you exported has no directional information, so you will have to indicate them in the dynamic analysis when you perform it by Caesar. So let's bring Caesar here. We go to interfaces, we select AFT Impulse, we browse. The name of we exported is both. So here it brings us the force set that we exported. I'm going to apply it in node 45. And the second force set, I'm going to apply it in node 90. I say OK. It will tells me that it will create the DLF curve. So I say yes, yes. So now it's generating the DLF curve that it's going to be used to see how the natural frequencies dynamic load factor is applied, depending on their participation factor in the event. 52%, 60%, almost done, 70%. Ready. So it tells me, do you want to apply the dynamic input file? I said yes, create it for me. Generally, dynamic is applied to the same where you did the static analysis, so it's called Hammer. I said open. So it's ready. So now if I open the dynamic analysis, I go to analysis and I open, we can see that it exported the the loads application and dynamic load factor that it created for node 45 and 90. The force sets are already created, and the sense of the application is already here, -1 that we indicated when we created the impulse example. The spectrum load cases are also created, and the direction is already indicated here. So the only thing that you will need to do is in advance. This is something I like to do because this type of force excites several frequencies at the same time. So in this case, we go to control parameters. Caesar by default has 33 hertz. I wanted to to set up the frequency cutoff at higher. So I said 100, but this is a matter of preference of the pipe stress engineer. We run it. So this is the only change you have to make. It's ready to be analyzed. As I said, the cutoff frequency, I went over and increased it to 100. So now it creates a combination here. We check the combination, the stress factors here. We go over stresses. We look at the cases and we see that it's failing. It requires, in the first case, first source set applied in the first section of the pipe, the long pipe, and it also fails in the second section of the pipe. So we see the spectrum analysis very well set for CISA 2. It's easy. It's you only have to understand that you have to export it with the correct sense, and it will create everything for you. In this case, we use one pipe. If you have more than one pipe and you want to analyze and you want to calculate the intermediate forces, like here we have valves and sections, so we want to add this would be points of reflection for the wave. So here we want to calculate the forces, imbalance forces, and node 121 and 22, considering all these pipes at the same time. To do that, you would have to create a group here, and when you generate the forces, you, instead of using different forces like we use in the example that we created, we would use differences by plus 3 pipes and indicate the group that you created, so it will calculate all the pipes at the same time. So we come to the end of the part 1 of this webinar. Now we open the sessions for questions from the participants. Let me see the questions here. Can Waterhammer be mitigated by replacing a valve with a slow closing? Question. By replacing a valve. Let me see. I'm trying to see the questions here. It's closing, yes, it can be mitigated by the closure, but in this case, we're analyzing a pump trip. So a valve does not apply here because the event we're analyzing. But yes, if you're closing a valve and you close it slower, it can mitigate the effect of Waterhammer. In the slides, the deck available is this slide. Yes, the presentation is not available, but if you request it, I can send it to you. Can Waterhammer be mitigated by replacing? Okay. Please confirm if this is applicable for an underground pipe. Yes, it is. Like you can calculate the imbalance forces for underground pipe. So an underground pipe, the only difference is that the anchors, or you have a virtual anchor that's generated by the soil, but you can calculate the imbalance forces in the pipe that is buried for in the pipes. Can I import my Caesar 2 model into AFT Impulse and then perform an analysis? Yes, you can do that. As a matter of fact, I prepared an example here. Let me bring Impulse. Let me try to see if I have an example here that I can bring. Let's say new. To do that, what you do is in Caesar 2, you create a neutral file, convert neutral file, input file from input. So you create it from Caesar, and then in Impulse, I'm going to create a new one. You come here in Impulse and you say import pipe layout. You come from Caesar. Here you can import Hammer. As I said, I created a neutral file from Caesar. And here is a import file. So you can edit here and change. But yes, the answer is yes. You can import the input from Caesar, and so you say import, and you have your model. Of course, you have to tweak it because Caesar Impulse needs more information on the pipe. So now you might want to change the pipe, use a pipe material, but it imports the wall thickness is not imported, so you wouldn't have to do some tweaking, but the basic layout from Caesar is already imported into Impulse. Can you provide any criteria which pipe length diameter combination we should consider which may have significant impact in the Waterhammer force? Really, this is not an easy question because there's no rule to what combination of pipe length and diameter is applicable. And I would, having a tool like Impulse, I would look at all the forces and see how they last and analyze it. And doing a time history analysis would be easier, or a spectral analysis, you can create it and see, since it will create it for you, it's easy to see, but really establish a criteria for pipe length diameter combination that will help you, that will guide you. As I haven't seen one, but it's not easy to establish. Why the force direction is negative in the pipe stress program is because you are interested in the forces of the flow, contents and impulse, but intersects is in the force. The thing is, for impulse, it's positive in the flow direction. So you have to see the coordinates of the pipe stress program to establish the equivalence. That is why it's negative, because for CISA 2 in the x direction is opposite to the positive direction that is in impulse. Why two forceps? Oh, well, yes, because in this case, it's the longest pipe, so and longest pipe in the force and the legs when we smaller. Yes, this could be, or should normally, we should consider all the length. Well, let me answer this question here. Like, let me bring the example again. In this example, I analyzed the longest. And why? Because that's where the wave, the pressure wave lasts longer. So the imbalance force can cause more damage. This can be a pipe rack or whatever. And I want to design the directional anchors in this sense. Like I want to calculate, because probably we'll have to report it to the civil engineers. But if I have a hanger here, I would like to examine this section here, because it might cause problems, because this section here might have very low frequencies, and because it has a hanger, and a hanger is not a dynamic restraint. So it depends on the arrangement you have. But in this example, we picked these two long ones because generally, as I said, these are the longest one. They might be going up in a pipe rack, and I want to report to the civil engineers. But again, if there's a hanger here, and since hangers are not dynamic restraints, I want to examine this section here because it has very low frequencies, and very low frequencies are easily excited because they require less energy to be excited dynamically and show high movements in the pipe and create high stresses. Will rapid closing of any valve always create Waterhammer? Not necessarily. It depends on the pressure and the flow that you're handling. And another thing that is important, maybe closing a valve generates Waterhammer, but the magnitude of the overpressure is not high enough, so it's not a problem for you because the piping handle it easily. So not necessarily the appearance of Waterhammer is a problem unless it doesn't comply with code, either B31.4 or B31.3. The stresses generated if you're using B31.3 are not high enough, so you can live with the Waterhammer problem that's happening in your pipe. Okay, so this is, let me see if I have more questions. It would be great if you share the recorded webinar link afterward. Yes, you will receive an email with the recorded webinars that you can watch. And if you have any questions, feel free to ask, send me an email. And yeah, like you can model your underground piping and calculate the imbalance forces, because for impulse, whether, and also you can indicate an impulse whether it's buried or not. Let me check that. Yes, you can indicate an impulse if it's buried, and it will calculate the wave speed different in that section of the pipe. Yes, you can calculate the imbalance forces due to change of speed or trip in the pump, and also it has if it's going to be, you're going to have reverse flow and it's going to act in the 4 quadrants. You have the models and impulse that allow you to model that. Is it possible to place the force sets by hand in the program other than Caesar? Yes, well, it depends on the program you're using, but like the the force set, you can import it when you do the export the. Let me bring impulse, the graph results, force sets. Let me generate one. I'm going to generate it for 1 second. So now you can come here and say, copy XY that data in and when you open the Excel file, you can paste it here. And here you have the file, and you can apply this file to any pipe stress program and export it and save it and apply it to any pipe stress program, not necessarily Caesar too. Do you apply the same process for gravity? Yes, it's the same process. If it's moved by gravity and you have a Waterhammer event happening, it's the same process. One question, how do you find solutions with a Waterhammer failures? It completely depends on the engineer or any standard method like search tank. Yes, it depends on the criteria of the engineer. Search tank is usually a good solution. It's easy, but sometimes it's not applicable or too expensive. So maybe handling with closing the valve slower or changing the profile of the closure of the valve will solve your problem. or there are really different solutions on it, and it depends on the criteria of the engineer that is doing the analysis. Mostly impacted are usually elbows. When you specify the entire pipe, do the analysis include elbows? Here, I established the elbows here. Impulse has elbows included now in the new version. Yes, elbows are more usually included, and I like to model it. And but yes, Impulse does include elbow, and we can model them now. Could you use the result from AFT static forces and elbows? Yes, you can do. What I would do if I'm going to do a static analysis, I would take this pressure here, this force here, and apply it to in a static equivalent analysis in Caesar 2. If I'm not going to perform either spectrum or history analysis, I'm doing the static equivalent. You can apply that force, the maximum force, to make sure you cover with a dynamic load factor of 2, because that's generally what is done. The force, you apply a dynamic load factor of 2, and you apply it in your static analysis. Yes, my presentations can be sent. Just send me an email, ronaldopinto@aft.com, and I'll send you the presentation if you require the model the same. Can you use B31.1 for this? Yes, B31.1 can be used for the analysis, and the same criteria as B31.3. B31.1 establishes a stress, maximum stress in the pipe. How this can be used for cross? I imagine cross, you're talking about crossing the change in direction in a pipeline when you cross a road or something. Well, the same way, like you have in the cross section, you have elbows. You can calculate the imbalance forces there and determine whether or not the forces are too high. If you're going to use a restraint directional anchors to control the high forces generated in the cross. Can we do this for steam piping? Yes, you can do steam blowing. We have a new program that's called Extreme. If you want to test it, we can. And steam piping is a challenge because calculating the imbalance forces in non-liquid and gas system is. But yes, you cannot use Impulse. You have to use Extreme, and Extreme can calculate the imbalance forces for you. Can we use AutoPipe to analyze those forces? As I said, yes, we're working with Bentley. We're trying to improve the interface. Hopefully it will come, and AutoPipe users will have the same interface that Caesar 2 users have to calculate the forces and apply the same methods. Any of the Energy Institute methods have taken in reference of AFT Impulse. I have a Weber and Energy Institute method for ARV and acoustic induced vibration and force induced vibration. Take a look at it, and yes, we do have Energy Institute. Acoustic induced vibration is a big problem. We have developed an Excel interface for that application. Feel free to look for my webinar on AIV and FIV, and the same. We do have an application for that. It's very interesting. We can send you the Excel file that is needed to do this check. See submerged piping. I have very little experience in submerged piping, but the forces applied, how they apply in the submerged part, but you can calculate the imbalance force in the section, but maybe the pressure wave speed changes. I really don't know, but if you have an application, we can look at it to see. Would you say that response spectrum analysis versus time history analysis will tend to overestimate dynamics forces for shock loads as per your example? I think that time history analysis is more accurate, and now that we have the computer capability, it's worth doing it. But spectrum analysis has been useful all the time, so it really depends on your criteria whether to use one or the other. I don't think that spectrum analysis is obsolete. It's useful, but we have to understand the limitations of using it versus time history analysis. In my case, I prefer to do time history analysis, but spectrum analysis is also useful, especially if you have dynamic isolation by anchors, that one force doesn't affect the other. Well, there are many questions. We come to the end of the section. I'll look into the other questions. I'll try to answer, and I'll send you a response to all the participants. Thank you very much for joining us. Hope you can join us for future webinars. My name is Ronaldo Pinto. My email is ronaldopinto@aft.com, and you'll receive an email with the link to hear the recorded webinar in this section. Thank you again for your participation. I hope you see you in future events.